All right, this is our intro video for AP Calculus AB, section 1.4. We'll be looking at one-sided limits and continuity. So let's look at some notation here first. I want to show you this first notation here. It is the familiar LIM with x approaching 1, but then almost like kind of an exponent, sort of a superscript. We have a little plus sign of f of x, so that means the limit is f of x as x approaches c from the right. So if you're approaching from the right, this actually can be a little confusing. If you're approaching from the right, you're actually moving left. Makes sense? So we're approaching from the right. And then the notation for the limit of f of x as x approaches c from the left would be the exact same thing, but instead of a plus sign, we would have a minus sign. I'm just looking at what I wrote earlier. I don't know why I wrote 1. It should definitely be a c. So let's try that again up there. So limit as x approaches c from the right. Sorry about the confusion there. So those are some notational items that we want to make sure that we're really good at. We're going to use those moving forward. So let's take a look at our example here on this page. It's based on a graph. It says find these 5 things here. So I would suggest, if you want, pausing the video and trying these on your own, or simply watch the video, however you think you're going to learn best. So the first thing we're supposed to find is f of negative 7. So as I count over there to the left, I see that negative 7 is there as far as an x value. So f of negative 7, this is not a limit. This is simply asking, what is the value of the function when x is negative 7? Another way to think about it is, if I input negative 7 in for x, what do I get out for y? We're actually going to be looking at this point up here, right? That's the actual output for an input of negative 7. Now we see the function as doing some interesting behavior down there, and we can deal with that when it comes to a limit, but we're actually looking for the value of the function when x equals negative 7, and it looks like that is 3, 4, 5, 6, looks like that's 7. And then we'll do the following limits. So the limit as x approaches negative 7 from the left. Well, what I'm going to be doing is I'm going to get to the left of negative 7. So as I approach from the left, what is the y value that I'm getting closer and closer and closer to? Well, it looks like I'm getting closer and closer as I get closer and closer to negative 7. Looks like my y value is getting closer and closer to a height of 3. Now as I do the same kind of thing, I'm going to approach this time from the right. This is number 3. So as I approach negative 7 from the right, you can see that I'm getting, the y value is getting closer and closer to a value of 3. Let's switch over to the other side of the graph for numbers 4 and 5. Numbers 4 and 5 say the limit as x approaches 4 from the left. So 4 is right here, the x value of 4. So as I approach 4 from the left, let's think about what y value I'm getting closer and closer to. I'm getting closer and closer to a y value of 1. And then finally, number 5, limit as x approaches 4 from the right. So that would be from the right here, I'm approaching 4. I'm not getting closer and closer to a y value of 1. I'm actually getting closer and closer to a y value of negative 4. As you can see, this y value is about negative 4. So we're seeing some different behavior from the left and the right. So we could say that, of course, that the limit as x approaches 4 doesn't exist if we connect that back to what we talked about in sections 1.2 and 1.3. Okay, we are going to conclude our video here talking about continuity. So to say that a function is continuous at x equals c means that there is no break or interruption in the graph of f at c. It means the graph is unbroken and there are no gaps, jumps, or vertical asymptotes. We've looked at those before, but now we're going to look at it in terms of continuity. And continuity is an important thing for us to consider. Almost all the things that we're going to look at in the future depend in large part on whether a function is continuous or not. And so let's take a few minutes and look at this. This is definitely a key point in what we're doing here. So a function is continuous at c if all 3 of the following conditions are met. F of c is defined or you could say f of c exists. The limit as x approaches c of f of x also exists. Of course, what that means really is that the limit as x approaches c from the left is equal to the limit as x approaches c from the right. So the behavior from the left and the right have to be the same. The function has to be defined at c. And finally, number 3, the limit as x approaches c of f of x has to equal f of c. So each of these 3 parts basically deal with a different type of discontinuity. Part 1 guarantees that there's not a vertical asymptote at c. Number 2 guarantees that we don't have a jump at c. And number 3 guarantees that we don't have a removable or a gap discontinuity. We'll talk about that here in a second. So limit exists if and only if the left and the right hand limit agree with each other. But we will typically use this format I'm about to write here to prove or show continuity of a function. We're going to say the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x is equal to f of c. If we can say that statement, if that statement is true, then we know for sure our function is continuous at x equals c. A little more terminology here. Discontinuity is a point where the function is not continuous. We're going to look at a couple of examples of that. So the graph on the left, you can see clearly there's a point of discontinuity right there. There's some people would call that a hole or maybe a gap. We're going to call it a removable discontinuity. The reason why we would call it removable is because if we just redefine it as a piecewise function, we certainly could fill that gap. We could fill that hole and create a continuous function. So that technically is a removable discontinuity. The second one on the right there is also a gap or a hole. You can see right here we have another point of discontinuity. And I would say again that is removable because we could, if we wanted to, just redefine the value of the y value of that point and move it down, move it down in there to fill that gap. All right, we've got a couple more here. The one on the left, we would call this a jump discontinuity. A jump discontinuity is not removable. You can see right in here, looks like x equals -6. We've got a jump. So one way to define a jump would be to say the limit as x approaches -6 from the left of our function does not equal the limit as x approaches -6 from the right of our function. That is what defines a jump discontinuity. We also have on the right a different discontinuity. This would be discontinuity due to a vertical asymptote. You can see it looks like we have right in here, we have some something characteristic of an asymptote, and so it looks like we have a discontinuity there at x equals -2 because of that vertical asymptote. There's one other way this could look. I just thought I'd sketch this out for you. Down here on the bottom, we could have a vertical asymptote looking function. Maybe we have a vertical asymptote at +2 on this one. And we could have the function coming in doing that and that, something like that. But then, perhaps there is a piecewise part of this graph where f of 2 is 3. So this would still be a vertical asymptote. This would still be non-removable, but that's just one more possible way this could look. There are certainly other ways as well, but those are our 3 major classifications: removable, jump, and discontinuities due to vertical asymptotes. All right, we'll get into this a lot more in class, but I want to do one question to check your understanding here and kind of get you in the frame of thinking that we're going to be taking in class. So this question says, prove that f of x equals, that piecewise function there, prove that it is not continuous at x equals 2, and then it wants us to classify that, I guess it should be discontinuity right there. Let me cross that word out. Discontinuity. Is it removable, a jump, or is it due to a vertical asymptote? So if you remember from earlier in our video, if we're trying to work with continuity or prove discontinuity or prove continuity, whatever it might be, we're going to start off with that basic framework of the limit as x approaches something, in this case it's going to be a 2 from the left of our function equals the limit as x approaches 2 from the right of our function is equal to f of 2. So here, because we're asked to prove that this function is not continuous at 2, then we will actually be looking for the statement to be false. So what I'm looking at here is I see x is greater than 2. That tells me that this is the right piece of my graph, and the other one is less than or equal to 2, so that tells me that that part is the left part of my graph. So when I try to construct this statement, all right, we will do some examples like this in our class next time, but I thought we'd do a little check for understanding along those lines, just to at least get you thinking along the directions that I want you to be thinking. So this question, checking for understanding here, says, prove that this function here, f of x, is not continuous at 2. It wants us to classify that discontinuity. It's a little typo there. I should say discontinuity. As removable or a jump or due to a vertical asymptote. So, if you remember from earlier in our video, I talked about if you're ever trying to prove that some function is or is not continuous, we're going to always start off with this statement right here. Limit as x approaches, in this case we're going to use a 2, that's the point in question. Limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x is equal to f of 2, the value of the function at that point. So again, what we're basically saying is that the left-hand behavior and the right-hand behavior are the same, and those two left-hand and right-hand behaviors are equal to the actual value of the function at that point. So since we're trying to prove that this function is not continuous, we're actually going to try to make this statement, see if it's false. So here's what we do. I'm going to look at my piecewise graph here, and I'm going to notice x is greater than 2. That tells me that this is the right part of the graph. And because this is x is less than or equal to 2, that is the left part of the graph. And so I'll use that as I try to work with my limit statement here. So limit as x approaches 2 from the left, well, I'm going to go ahead and use that line, the part that's from the left. So it's going to be the limit as x approaches 2 from the left of negative 4x minus 1 is equal to, now this other part, the part that's from the right, I'm going to use my right part. So that would be the limit as x approaches 2 from the right of the quadratic there, that parabola, 3x squared minus 7. And that's equal to f of 2. Did you notice the or equal to there on the x is less than or equal to 2? Well, that means that that part actually contains f of 2. And so that's the line. So I would write negative 4 times 2 minus 1. So like with any other limit we've looked at, the first thing I want you to think about is, can I just directly plug in my limit? So I'm going to try that. So it would be negative 4 times 2 minus 1. That's my attempt to evaluate the limit from the left. The limit from the right would be 3 parentheses 2 squared minus 7. And of course equals, that is negative 9. Okay, so I'm going to just evaluate these. We already know this is negative 9. We know that that's negative 9. And then 3 times 4 is 12, minus 7 is 5. So we've actually proven it. We've proven that the behavior from the left and the right is not the same, and so therefore we can say f of x is not continuous at x equals 2. And because the behavior from the left and the right is different, we can say that it is a jump discontinuity. It might be helpful for you to graph that and kind of see a visual on that. We'll do some of that in class for sure, but definitely going to be a jump discontinuity because that left-hand and right-hand behavior is different. So, see you in class. We'll work on some more of these examples when I see you then.